So we saw in a previous video how a recurrent neural network could be used in a certain structure to solve sequence-to-sequence problems. So those are problems where the input is a sequence of one length and the output is a sequence of a possibly different length. And the important thing is that you need to have seen the whole input sequence before you're able to start producing the output sequence. So the way these sequence-to-sequence networks work is they begin with a many-to-one encoder. So we have many outputs. That's our sequence of input vectors, x1 to xt. And the result of that is to output the final hidden state at time t. And then we decode to get our output by using a one-to-many recurrent neural network. So this decoder takes the initial state is the final hidden state of the encoder, and this network at each time predicts the next its own hidden state, and it outputs a token for each of those hidden states. And usually you would output some special token to mean that's the end of the output and you can stop at that point. And importantly, these two networks, so the recurrent network and the decoder and the encoder, they're different and they use different weights. So let's dive in and see how such a sequence-to-sequence network would be implemented in a bit more detail. So in this case, we're dealing with the task of translating from English to Spanish. So the input vectors are embeddings of tokens of the English language. In this case, they're just words. So each word has been embedded to a vector, and that's the input at each time, and we feed those in sequence. And then in the decoder, we're going to output probabilities over all of the words in Spanish. So here, the most likely Spanish word for the first word of the sentence was this estamos. And after some series of output steps, the decoder decides that's the end of the sentence and it outputs this end of sequence token. So concretely, the input here is a sequence of vectors x1 to x capital T, and the output is a sequence of a possibly different length, t prime, and each of those y's are weights that correspond to probabilities over your set of output tokens. So the encoder is a function that takes the previous hidden state and the current input token, and it predicts the next hidden state of the encoder. And then the decoder is a different function with different weights, and that takes its previous hidden state and it outputs two things: the next hidden state and also the output token for the current hidden state. So in practice, rather than trying to pass everything through that final hidden state of the encoder and then hoping that the required information makes it all the way through the hidden states of the decoder, a better thing to do is to take the final hidden state of the encoder and from that predict the initial decoder state, S0, so usually that would just be some linear transformation, and also this thing called the context vector C, and often C is just the final hidden state of the encoder. And the purpose of the context vector is to transfer information from the entire encoded sequence to every part of the decoder output. So at each time step, the decoder gets access to all of the information from the encoder without some of it potentially having been lost through this sequence of decoder hidden states. And this works better than just simply passing only the initial hidden state. Now the problem with this is, even in this modified setup, the context vector is still acting as a bottleneck. So if the entire encoded sequence is very long, so T is very large, then we have to compress that entire sequence, all of the information, into C. And C will usually be a vector with dimension in the tens or maybe hundreds, but T could be very large. It could be thousands of words in the input. So the solution to this is to use a different context vector for each decoder time step. So what that will do is it will allow us to pass different information about the encoded input sequence to each step of the decoder output. So for example, if I'm about to output something here, maybe outputting this second word means that I should make use of particular information, let's say in the first and third word or something like that. So we'll now see a modification to this architecture that allows us to do that, and it's a step towards a mechanism called attention. So our starting point is the encoder as it was before. So we have our input tokens, our encoder hidden states, and the final hidden state is used to predict the initial state of the decoder. However, what we do now is we compare the current hidden state of the decoder with each of the hidden states of the encoder, and we do that by passing them to this function f_att, which is usually just an MLP, and it outputs a scalar value. Now what this scalar value is telling us is at time step t, the alignment score ETI is saying how important is the ith hidden state in the encoder for predicting the output at time t. So for predicting the hidden state of the decoder at time t. So we take these scores, which are telling us how important each of the hidden states is in order to compute the decoder output at this point, and we now pass them through a softmax function. So all that does is, instead of these raw scores, which could be any value, positive or negative, unbounded, we now have a set of values A11 to A14, which are between 0 and 1 and sum to 1. So we can use these as weights to combine the encoder hidden states. So we multiply each encoder hidden state by its corresponding attention weight, these A values, A11 to A14, and then we sum all of them across all of the hidden states of the encoder, and we use that to give us the context vector at time t. So we can see the context vector at time t is simply the sum of the attention weights multiplied by the corresponding hidden states. Right, now we're ready to start using that in the decoder. So the decoder, in order to compute its hidden state at time t, will take the previous input token. So in this case, to kick it off, we're just going to give it this start token y0, its previous hidden state, which in this case is going to be initialized from the encoder, and this special context vector, which is specifically for this time, and that's allowing it to pick out important words from the input sequence. So from the decoder hidden state, we can then transform this to our output. So that would be now the probability distribution over all of the words in Spanish, and the most likely one is this word estamos. So the intuition here is that the context vector is attending to relevant parts of the input sequence. So in this case, the word estamos roughly means we are. So it's very likely that the attention weights for the first and second input tokens, so here, will be very large, whereas the attention weights for the third and fourth input tokens will be really small, and it's basically ignoring them. So what we can infer from that is that the initial state of the decoder, its hidden state, was somehow quite similar to the hidden state at time 1 and 2 in the encoder. So we and R had hidden states similar to this initial hidden state, and that meant they ended up getting high attention weights, and the first context vector was heavily influenced by those two, and that led it as a first word to produce the output estamos. Okay, so we can now take this this output for time 1 and use it as the input for time 2. We need a new context vector. To get that, we take the hidden state of the decoder from the previous time step, so that's now S1, and we use that to compute attention weights. So now we're comparing S1 to all of the hidden states via the FATT function. That gives us these weights. We softmax them. It gives us attention weights. We recombine the hidden states using these weights, sum them, and that gives us our next context vector. So that goes into the decoder along with this next token, and from there we can decode and we get the next word. So basically we can just repeat this process, use the previous hidden state of the decoder to compute the next context vector, and then use that context vector to compute the next hidden state and the next output. And the output here, comiendo, roughly translates to R eating. So we might expect that the attention weight applied to the input token eating is going to be very high, so it's 0.8. But also this second token, so the attention weight 2.2, is reasonably high because this word is kind of conveying R eating, whereas we and bread would get a very low score because they're not relevant here at all. So we end up with a hidden state that's mainly influenced by eating and also R somewhat, and when we decode that we come out with this Spanish word comiendo.